Hello everyone and welcome to the Civil Engineering Essentials channel. I hope you enjoy the video. Alright, so in this video we're going to dive into something called the Finite Element Method. And now whether you are an expert in finite element or a beginner, there will be something for you in this video series. Although I want to mention that I will try to simplify the explanation as much as I can, because I want to keep it compact for a YouTube video form. However, for the interested people among you, of course, there's a reference where there are really good information that you can take a look on, and of course, follow our lectures while we are progressing. My reference in this video series is gonna be a book called a first course in the Finite Element Method. This is the 6th edition from Daryl L. Logan. Of course, if you want, you can take any recent edition, but I'm gonna rely on the 6th edition because it's the book I have with me. So today we're going to give an introduction about the finite element method. I hope you enjoy. Alright, so to start with, I'm going to of course reference here chapter 1 in the same book I mentioned before, and we're going to talk about the introduction. Now at the end of this video you should be able to understand some basics of the finite element method, understand what a matrix is just quickly, basically see the general steps of solving problems in the finite element method, see some elements, and understand some advantages of the finite element method. Alright, so going on, well, first of all, finite element method, what gives? Why is it called the finite element method? I mean, the name sounds cool, and the abbreviation FEM is something you will hear a lot, but why? Well, I want to discretize the name, basically. It consists of three words, finite, and the idea of talking about something called finite is because in real life, your elements are actually something called an infinite continuum. Basically, you can zoom in as much as you want, and no matter what happens, you have an infinitesimally small element, meaning that your continuum or your domain here is actually going to be an infinite number of elements, and that's the reason why you're integrating stuff usually, because you're summing up an infinite number of elements. Now, the finite element method basically takes this infinite continuum and tries to approximate it by converting this into a finite number of little pieces. And that's why we call it finite. Now, why is it called element? Because, I mean, those pieces are called elements. So you are converting the infinite domain or infinite continuum into a finite number of elements. Of course, the word element here is because you have multiple possible elements. You see, when you discretize a continuum, you have some elements to choose from. You have linear element, planar element, and even volumetric elements, and of course those elements are our building blocks, and that's why it's called the finite element method. And why method? Because, I mean, it's a method, right? So there is nothing to explain here. So basically this is why it's called the finite element method and the idea behind it. Now, furthermore, what is the general idea of finite element method? Like, why do I need this? The reason why I need this is because the alternative is gruesome. The alternative is to be talking or dealing with a structure analysis problem as being something called an ODE or PDE, an ordinary differential equation or partial differential equation. Generally, they are DEs, they are differential equations, and they take a lot of crazy forms to begin with. For example, this here is a fourth degree ordinary differential equation for the beam column element here. A beam column element is an element that has shear forces, which means moments also, on the transversal load, and of course, an element that has transversal loads and axial loads. And this is no joke to solve. I mean, it looks cute, and maybe you can solve it. But of course, if you go deeper and start talking about basically some planar elements, this becomes really hard to solve. Also, this is just one beam. What about if I add another column here with a fixed support here, for example? How would you solve that thing now? Because suddenly your change in y, which is deflection, with respect to x is not only related to this element, but related to this element too. It becomes really hard to formulate problems like that. This analytical way of solving works only for the simplest of problems, and that's the reason why, well, we needed the finite element method. Now, what is the idea of the finite element method? The idea behind it is, first of all, to understand that the analytical solution might be a nightmare to solve, and is even, I mean, this problem is not computer friendly. Like, a computer just doesn't know how to deal with that stuff. I mean, yes, there is something called symbolic math in MATLAB, which is cool, and this is something maybe the PhD and MSc students know about. It's called symbolic math. I think if you type Sims X in MATLAB, you get the access to the symbolic math toolbox, which might work, but on the simplest of problems. However, I digress. This is not computer friendly, so we don't need this. Also, finite element is kind of cooler. So what's the idea? The idea is basically to discretize the element into little pieces and approximate that. So this is an approximation of the solution of the ordinary differential equation. It's an approximation because now you are assuming that the solution is, for example, in our case here, a linear function. We're assuming that you have a linear function between each of those two nodes. By the way, those points are called nodes, something you see in Autodesk Robot. And I'm doing, of course, on this channel, Autodesk Robot tutorials. I'll link it here, basically. Those are called nodes, and those are called elements. And, well, those elements approximate the movement or deflection of the entire beam. Now, you can see that this is kind of piecewise in nature, which is not exactly the same as the real deflection. The real deflection would be a smooth parabola or a cubic function, whatever it is. So you are basically paying the price in terms of accuracy. Does this mean that the finite element method is an approximate method? The answer is yes, 100%. The finite element method is an approximate method. It's not an exact method, but it's a good approximation. Now, of course, we can improve the accuracy of those finite elements, and this is where something called H refinement and P refinement comes into place, and something called R refinement, which I will leave for the interested to read about. Now, before I continue, those names, H refinement and P refinement, look, before I continue, I want to tell you the strategy and the philosophy of my teaching in universities and my teaching here on the YouTube channel. My philosophy is not to basically throw some cool words at you and speak with those amazing words like improving accuracy using the H refinement and P refinement. I mean, this makes me sound cool and smart, but it might confuse you. My approach in teaching here is basically to try to explain the stuff using the simplest of possible words, because my goal here is for you to become smarter, not for me to sound smart. So, okay, what is H refinement? I mean, forget about this. Let's forget about everything here. Let's take a look here. Just think about it. How could you improve the accuracy of this approximation? Let's say that this is the real deal, and you want to improve the accuracy of this approximation. Of course, first of all, you can discretize it using more points. If you use more points here, your lines approach a parabola. Allow me to explain. If you have a parabola like this, if you are using 2 points like this, then there is a big margin of error between what your approximation is, that's your approximation, and what the real deal is. Now, if you use 3 points to approximate the parabola, 1, 2, 3, then you can see that the margin of error is decreasing. The area that seems to be the error is smaller when compared to this one because you have more elements. Now, of course, if you discretize more elements, you would get a better accuracy. So you would think, wait a minute, this means I can make my elements really small. Well, the problem is that if you have more elements, there is more calculation effort involved. And you can see this in Autodesk Robot when you switch to the fine meshing option, something that we discussed in this lab series. I will link here above. Yes, I am a channel in the end, and I want to link to other videos so that you can get the full benefit of the entire channel. So, okay, that's the first option of improving the approximation. What is the second option? The second option is basically not to use lines, but to use parabolas in the approximation. Like, who said that this should be a line equation between those 2 points? I could assume a parabola, for example, here, a second order equation. Now, this is something we call instead of adding more nodes, you can improve the deflection approximation between 2 adjacent points. Have you ever done this before? Well, outside the finite element, yes, you have done this in something called the Simpson's 1/3 rule versus the trapezoid rule when you were approximating integrations. Of course, we're not approximating integrations here, but the idea remains that if you use a higher order curve between nodes, then your accuracy will increase. Now, those are technically called or referred to as H refinement, which means more points, or more lines, and P refinement, which means the polynomial refinement. The polynomial refinement here is basically that we are increasing the degree of the polynomial. Instead of a polynomial where your y equals x plus b, for example, or ax plus b, this is a power of 1, you increase to power of 2, which means a parabola. Now, we need to talk about matrices here very quickly. Now, finite element methods rely heavily on matrix algebra. But of course, to deal with that, we need to understand what matrices are. And to answer that question, well, here it is. Now, matrices are not those boxes with cool and magical, mystical properties that are used in Gauss eliminations and LED compositions? No. Matrices are not mystical boxes that just stuff happens inside. No, matrices do actually have a mathematical meaning, and the mathematical meaning is that a matrix is just a cool representation of a system of equations. That is all what a matrix is. A cool representation of a system of equations. That is what it is. Now, of course, that's a noob's way of writing the name. Actually, why we use matrices is because, well, they are pretty good in terms of computers. Computers are really good. They excel in dealing with those matrices. Instead of computers dealing with this kind of stuff where you have those ODEs where computers do not work with, computers are really powerful when it comes to matrices. Well, let me just also give some hashtags out. I want just to hashtag numerical analysis, if you remember that, LED composition and Gauss elimination. Those things work on matrices, and finite element methods rely heavily on matrices. All right, so I hope that makes sense to you. Going on with this, we need to talk, of course, about the finite element matrix itself. Now, this is one of the fundamental matrices you will see in the finite element method. Now, for the Master of Science people and for the PhD people, they know that this is a lie. They know that the actual dynamic finite element matrix or system of equations is actually mass as a matrix multiplied by something called x double dot, which is the acceleration, plus c, which is your damping matrix, multiplied by x dot, which is your velocity, plus k capital, which is your stiffness matrix, multiplied by x equals the force. That's what the dynamic equation is. Now, we are not in dynamics, we are in statics, so we do not have any acceleration or velocity, and that's the reason why you get back to the original statics finite element method. Just saying that, hey, there is further reading for Master of Science and PhD dudes, but for us here now, we are going to talk about the simplistic finite element for statics. Now, the finite element method means that for each force, that the force vector is going to equal the stiffness matrix multiplied by the degree of freedom vector. Let me reiterate here. The force is here, well, that's a force vector, and I'm here stating the obvious. The matrix here is called the stiffness matrix, and you will hear about this a lot. Like maybe around 90% of the course is going to be talking about the stiffness matrix and how to assemble and deal with that thing. And finally here, you have the movements or deflections, which are called the degrees of freedom. We're going to talk about later what degrees of freedom mean, but basically those are possible movements of a point because some movements are restricted. Allow me to explain very quickly. If you have a cantilever beam like this in a two-dimensional setting, if you have a point in a two-dimensional setting, what are the possible movements of a point in a structure? It could move in the x, it could move in the y, and it could rotate around the z-axis. In a 2D problem, those are three modes of movement. Now, how many modes of movement are actually allowed for that structure? In this case, the modes of movement allowed are only three modes of movement here, because this point could possibly move in the x due to the extension of that bar. It could possibly move in the y due to the bending of that bar, and it could also possibly rotate due to the bending of that bar. So the number of degrees of freedom here are 3. You would think, wait a minute, what about this? Well, this is a fixed support, so of course it cannot move in any direction. So basically you have 3 degrees of freedom. Now in 3-dimensional problems, you have 6 degrees of freedom per node, not 3, because suddenly in 3D you have movement x, movement y, movement z, rotation x, rotation y, and rotation z. So it becomes a little bit more complicated. But this is something that we'll talk about later. So I want us to hold on here that the degrees of freedom are the possible movements that the structure can move, and the idea here is to calculate those displacements based on the force and the structure. All right, fantastic. So going on with this, how do we go on with the analysis of those structure? Well, assume that we have this little cantilever beam with a force here, just to show something for it. So this is a cantilever beam with a force here, so how would I analyze that thing? Well, first of all, I need to decide, and I need to discretize it and select my element type. This is a decision, and of course here, the result of this discretization is going to be elements and nodes. And nodes are your calculation points, because the results you will get from the finite element method, the displacement vector you will get is going to be the displacement of each of those nodes on that structure. The displacement within those nodes is something we'll cover later using something called the shape functions, but of course, those are cool words for something I will explain later. Some people call it the interpolation functions. That's knowledge for later. Trying to keep things as simple as possible for an introduction, the challenge you would face here is to choose a line, area, or volume, how many elements you want, and the accuracy. Now, of course, you could choose a line element like this, which is here you have linear elements. Here you have planar elements or area elements, and here you have volumetric elements. Of course, each element has its shortcomings and its benefits. And you can see that the more you go deeper, the higher the calculation effort becomes. And for an introductory lecture, I will keep it as is right now. Going on further, you need to choose something called the displacement function. I will explain this later, but for now, I want to tell you that a displacement function is a function you assume your displacement to be. Allow me to explain. See, the original displacement function, in this case w, was an ordinary differential equation. Now, we don't want to solve the ordinary differential equation. We want to solve it in a simplistic finite element fashion. So I need to approximate this, and it is exactly this. This approximation of the real deflection shape is what makes the finite element method an approximate method. And of course, in this case, you could approximate using a polynomial. More to that later. The reason why we use polynomials is because 1, they are continuous on their domain, and 2, they are easy to be derived, and 3, of course, they just work well and easy in the mathematics. Do you have to go through the entire pain of choice and displacement function? Well, it depends on your level. Well, if you are a Bachelor of Science level, then no, you don't need to go through the pain of choice because the work has been already done for you by other people like Master of Science and PhD guys. You just know that if you have a beam like this, you should choose a line element with the following displacement function. So those things become some kind of obsolete for you in the Bachelor of Science level. If you are a Master of Science level, then yes, you would have to choose the correct displacement function because maybe you want to do some research where you want to basically find the function, an element, that gives you maximum accuracy. Whereas in the BSc, you're just using something called the engineering accuracy, a fair accuracy, a good enough accuracy in the BSc. In the MSc, you want to have the max accuracy as part of your research that you might be looking for. Of course, in PhD level, like this is the ultimate level, of course, bro, I feel your pain here, because in this case, everything goes out of the window and you have to create your own path. You have to create your own element and your own choice from scratch. And if you are interested in doing a PhD in finite element methods, then, well, welcome to the club, bro. All right, so let's say we want to analyze the beam here and we want to continue. Now, you need something called the strain displacement function and the stress-strain relationship. This is something that might be strange in the beginning, but later we'll get to understand why we need that stuff. In short, you studied mechanics of materials or strength of materials in other domains, and you know that epsilon equals change in length of x, and sigma equals E multiplied by epsilon. This is Hooke's law. Notice the limitations here. There are multiple limitations. Just by writing those two equations, you are imbuing or invoking multiple limitations. The first limitation you're invoking here is that you're talking about small displacements because large displacements might have different elements here. The second thing you're invoking here is that you're talking about geometric linearity and you're talking about material linearity. And of course, in the simplicity here is linear, straightforward, nothing here. Nonlinear becomes a little bit tricky, and of course, on the PhD level, well, rest in pieces. Not peace. Now to continue, we need to derive the stiffness matrix. The stiffness matrix answers the following question. If you have an element with forces F applied on the element, what is going to be the displacement X? And the relationship between the force and the displacement X, or some people call it D, is basically achieved by something called the stiffness matrix. Remember, this is just a system of equations, and you need to calculate this from the element you have. And this is derivable. Now, it can be derived by something called the direct method, by the variation method, and something also by the penalty or Gagliaking method. Those are really, really cool methods, but I will not be talking about them today because it's an introductory video. Now, are you going to derive those every time? The answer is depends on your level. If you are simply a BSc level dude, then no. There is a library of ready-to-use stiffness matrices for simple elements. If you are also there are softwares who do the job for you. If you are a Master of Science level, then yes, you will have to derive that stuff, because if you want to implement your own code, the shell elements, for example, are isoparametric element formulations, meaning that the stiffness matrix is not just a ready-to-use library. However, it's going to be depending on the shape of that isoparametric element. And I've talked about this in my video series, Autodesk Robot, when I was talking about the effect of mesh on the results, and I will link a video on the top right. In PhD level, once again, I feel you here nothing works, because literally your elastic modulus changes because you are talking about material nonlinearity, which means that this equation doesn't hold true, so nothing holds true. And you have to start doing Newton-Raphson calculations using something called load steps, because you want to calculate the deflection for each load step. I'm not making things up. Google it. All right, now we continue our steps. Step 5 is, well, I have the stiffness matrix of one element, but remember, I have discretized my beam into multiple elements, so I need to find the stiffness matrix of the full beam. This is something called assembly of global stiffness matrix. It's not as easy as it sounds. There are some transformations involved here, but this is for later. Part 6 is solve. Well, f equals kx, so find x. Now, and this becomes a no-brainer. Part 7 is post-processing. You have the displacements. You can calculate all the juicy results like bending moments and so on. And this is something we'll talk about later. However, I just said solve the displacement and just winged it, saying that, well, you have f equals kx. Now, what do you know? F is known in a problem because you have a structure under forces. K is known in a problem because you have the structure. And X is what you try to calculate. This is something called forward analysis, because the force is known, the structure is known, and you look for the displacement. There is something called inverse problems. This is PhD stuff, where you have the forces, have the displacement, and you are looking for the structure that caused those displacements. Now, this is a little idea for you, dear MSc and PhD guy. This is something called structural identification, which is used in something called structural health monitoring, where your goal is to find the stiffness matrix and the mass matrix and the damping matrix that provided the structure with the given response. But now, for our normal level, we have the force, we have the stiffness, find x. Now, it seems to be simple, but it isn't. If you are on the bachelor level, you are using softwares. If you really are interested and you want to implement your own MATLAB code, for example, then you would just invert the matrix and pray to God everything works out. If you are at a Master of Science level, you know immediately that x is going to equal the inverse of, or force multiplied by the inverse of k. Of course, left multiplication, right multiplication, I will leave it for you. But my point here is, you are inverting the stiffness matrix, and this costs a lot of calculation. So if you are aware of that, you would then go to something called LU decomposition, Gauss elimination, and so on, and you might have heard about something called preconditioning. If you are a PhD ultimate tier level, then you must know about something called skyline algorithm, preconditioning, gradient methods. I'm not making this stuff up. I actually programmed that in Strado, the software I'm still working on. So it becomes really interesting. Now, for now, I will not be talking about the solving of those equations now, maybe in the future. So, well, those are the steps. Now, of course, it's annoying because it seems I need to memorize those things. Now, do I have to memorize them? No. Look, I like to tell my viewers that we are not memorization machines. We are engineers. We are not calculators. We need to understand everything we do. So, with that being said, let's try to understand this in a logical sense. What is our mission and objective? Our mission and objective is to find those results, BMDs, SFDs, moments, and all those cool graphs. How can I find them? I can only find them if I have, and by the way, I'm trying to write the step beside each of those things. So this is step 7. Now, how can I find those juicy little information results? Well, you cannot find them unless you find the displacement at the nodes, which is step 6. And to find the displacement, you need to solve the equation, which is also why you need to solve this equation, which is still step 6. Now, what do you need for this? You need for this the stiffness matrix K, and that's why step 5 is needed. You need K, the stiffness matrix of the structure. Now, to find K of the structure, you need to find K of the element, which is step 4. Now it becomes interesting. Look, this is the element equation. F small being the forces on the element, X, or D sometimes, being the displacement of the element, and K being the stiffness matrix of the element. Now, how can you calculate that? Well, there is no simple answer for this right now, but I want to remind you that forces are related to stresses, and displacements are related to strains, and stresses and strains are related via Hooke's law, sigma equals E multiplied by epsilon. Now keep this tabbed, because here is the point. F is related to the stress and strain via the calculation of the stress and the calculation of Hooke's law and the strain. And that's the reason why step 2 and 3 were important, because in 1 you are assuming a displacement function, and in 2 you are trying to find the stress strain and displacement strain equations. What about X? Well, X is related to displacement, which is in turn related to the strain, and that's the reason why I needed step 2. So you see, those steps are not just something memorized, those steps are something that should make sense to you. Now, continuing, of course, nothing of that entire thing exists if you haven't finished step 1, which is basically to create your elements, right? Going on with this, there are some elements here. You have 1D elements, which are lines, you have 2D elements, which are area elements or planar elements, and you have 3 elements which are solid elements. Of course, you have some other elements like masses, rigid links, and so on, and this is taken from the following website, just in reference. This is where I took the graph. Of course, I know that there are some higher level people watching me. There's something called higher order elements, which basically means that your line now no longer is 2 points but 3 points, because you want to approximate a deflection shape that is a curve. But this is, of course, for you, secret. Now, the advantages of the finite element method, of course, first of all, let's assume that there are no disadvantages, LOL, but those are taken directly from the book, Director Logan. You can easily model irregularities, you can handle general load conditions. It's kind of cool. This is just recommended reading. I mean, look, if the finite element method was not such an amazing method full of advantages, then you would not have seen so many softwares that actually use this model or this method to calculate. If it was a garbage method, you will not see those cool programs. So that's testament enough, in my opinion. So yeah, that's everything I wanted to talk about in this introductory video. I hope that you enjoyed it and that it was beneficial for you. Of course, if you have enjoyed it, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.